Okay, so today we're going to do 2D vectors and relative motion. You're going to find that today's lesson is in many ways really similar to yesterday's lesson, for better or for worse. Yesterday's lesson was quite a gong show. Hopefully it won't be quite as long as yesterday's lesson, although maybe I'm going to end up eating my words here. I have no idea how long this will take, but we're really going to take the concepts that we learned yesterday and master them today. So we're really going to focus on building that. Here we go. So today's plan, quick recap of 2D vectors from last class. Just recall that 2D vectors are made up of X components and Y components. X components, of course, are left and right, or east and west, depending on perspective. And Y components are up or down, or in other words, north or south. Today, we're going to introduce the concept of relative motion. This is motion relative to things that are moving. Really, it's just an application of 2D vectors. When you see it, you'll go, oh, yeah, that's just what we've already been doing in a way. And then, of course, more practice time today. Anyway, let's get going. Start with some recap. So X and Y components, we'll start with an example real quick. I'd actually appreciate if you guys gave these a try. I'll read it first though. Suppose Andrew has walked a final displacement of 350 meters at an angle of 15 degrees south of west. How far west did he walk and how far south did he walk? I think we did one pretty much exactly like this last class. No peeking though. Pause the video here, give this one a try. All right, I'm going to go over this one now. So we, first of all, should probably draw this vector, right? Remember last class, I said this kind of stuff, the whole south of west stuff, that can often throw people through a bit of a loop, right? I always say focus on the second thing. That's where you're going first. And then it's 15 degrees south of that. So if I drew a line west, I'll even do like a dotted line here. If I was going west, I'm now going to go 15 degrees south of it. 15 degrees is not very much, so only go down a little bit and then connect that with a line. So 15 degrees is that way. And then we know the actual displacement is the 350 meters. That's your magnitude of that. What we're looking for is how far west did he walk? West is our X component. South in the second question is our Y component. Because X and Y are perpendicular to each other, we know we have a right angle there. Long story short, we know we can use trigonometry to solve for X and Y. So if we're looking for that X component, if we're looking for how far west he went, I want you to notice that in this right triangle that forms, 350 meters is your hypotenuse, X would be your adjacent side, and Y would be your opposite side, at least relative to this 15 degrees that you were given, right? If you think of trigonometry, you think of SOHCAHTOA. SOHCAHTOA, it's always useful to write that down. If we're looking for the west proportion of this, that's our adjacent side. And we already have our hypotenuse. Since it's adjacent and hypotenuse we're going to worry about cosine, because cosine is adjacent over hypotenuse. So let's write that out. Cosine of our angle, so cosine of 15 equals adjacent, which is X, over the hypotenuse, which is 350. To solve for X, we just need to multiply by 350 on both sides. So 350 times cosine 15 equals X. Let me throw that in the calculator real quick. As always, make sure you're in degree mode, please. There's no reason why it should have changed over, but it's always useful to double check. I get X equals, and it looks like we just want 2 sig digs here. I got 338, but that's just going to go to X equals, I'll have to round up, 3.4 times 10 to the 2 meters to the west. So that would be Andrew's west portion here. Next part, how far south did he walk? Well, this is just looking for the Y component. And in this example, the Y component is your opposite side. So we are looking for an opposite side. We have a hypotenuse. That's going to be sine, because sine is opposite over hypotenuse. So we'll say sine of 15 equals opposite, which is Y, over hypotenuse, which is 350. Multiply by 350 on both sides. We have 350 times sine 15 equals Y. Long story short, 350 times sine 15. Around 2 sig digs, I get Y equals 91 meters, and that'll be to the south. So 91 meters south. I think we did literally that exact same question yesterday. That's kind of weird that I have the same question 2 days in a row. Oh, well, whatever. It's good practice. It all works the same way one way or another. Hopefully this next question isn't a repeat either. Let's have a look. Okay, so this next one, suppose Jaden drove 12.5 kilometers 20 degrees north of west. How far north did she drive? How far west did she drive? I feel like this is a new one. Pause the video here, give this one a try on your own. All right, now that we're ready to go, hopefully on this one, as always, draw this. And again, what always stumbles people, at least in the past, is this whole north of west stuff. Remember, it's kind of backwards. Focus on the second one first. We're going north of west. So I'm going to draw west first, going west. And then we're going 20 degrees north of that. 20 degrees is not all that much, so I'll just do maybe like this far, and then draw your resultant vector. There it is. So that's 20 degrees north of west. Hopefully that works. Oh, and then we know the distance of that, 12.5 kilometers. If you prefer to change that to meters, go for it. But because all we're doing is trigonometry here, you don't have to change it to meters, but it doesn't hurt. Certainly doesn't hurt to change it to meters. If we were using kinematics equations like we were doing before, you'd probably want to. But in this case, it really doesn't matter. We'll leave it in kilometers. Anyway, so how far north did she drive? Well, that's going to be our y component here, right? So that'll be our north. X would be our west component. That'll be in the second part of this. If you notice with how this triangle is set up, your y component is your opposite side, and your x component is your adjacent side. It isn't always like that. It just usually is. Like, so don't go thinking that x is always adjacent and y is always opposite. You always have to build your triangle first and see where you're going with there, right? Clearly 12.5, that's our hypotenuse because it's across from our right angle. So let's just go to town on this one. Let's see. So north, that's our y component. That's opposite. If you think of SOHCAHTOA, we need to use our hypotenuse here because it's the only thing that was given to us. We're looking for our opposite. That's going to be sine, right? So sine of 20 degrees equals the opposite side, which is y, over the hypotenuse, which is 12.5. I won't even bother writing the next step. Hopefully you know the drill. We just need to multiply by 12.5 on both sides. So I'll go 12.5 times sine 20. And this is going to be our final answer for this part. And we need, oh shoot, we need 2 sig digs. That always catches us. You do have to use the sig digs in the angle thing. I know sometimes they don't, but it does technically count. Really, that's kind of annoying. But anyway, so to 2 sig digs here, I've got y equals 4.3 kilometers, and that would be north. There we go. All right, next one. How far west did she drive? Well, that's going to be your x component here. That's your adjacent. So adjacent and hypotenuse, this is going to be cosine, right? So cosine 20 equals adjacent, which is x, over hypotenuse, which is 12.5. Again, just using SOHCAHTOA, right? Multiply by 12.5 on both sides. So 12.5 times cosine 20. Once again, to 2 sig digs, that's going to be x equals, it's going to round right up to 12 kilometers. And that's 12 kilometers to the west. So kind of a shame that our sig digs here are just 2. I am like 100, not quite 100%. I say like 99% certain that does count for sig digs. Just, it seems really weird that all these questions we've used, it's always just been 2 there. It kind of throws the number off. For now, definitely just use those as sig digs. But I'm almost second guessing myself here, but I'm still pretty certain that does count. 2 sig digs, right? Because we did technically use that number in a calculation, so it should count. Anyway, that's just me talking to myself here. Anyway, moving on. Adding non-collinear 2D vectors. Ooh, this is that scary thing from yesterday. These take a long time. Just remember, when you are adding 2 non-collinear 2D vectors together, that's just like 2 diagonal lines together. The bottom line here is you have to figure out all of the x and y components of each of your vectors, make a whole sheet of them, and then combine them all together. So add all your x together and add all of your y together. If you have conflicting directions, like if one of your x's goes west and one of your x's goes east, you have to say one of them is positive and one of them is negative. And that's up to you to figure out which one is which. I always just say the positive one is the bigger one, but whatever, like it doesn't really matter, just as long as you keep track of it and know where your arrows are going. Once you have a total x and a total y, think of it this way, your total x is this way. I usually call that like x3. You could call it like x total if you wanted to, it's whatever, it's just up to you. And then you also need a y total or a y3, right? And that'll make a perpendicular angle right there, so 90 degrees, and then you just combine it with a final, oh my goodness, that was terrible. You combine it with a final resultant vector. That was slightly better, there we go. And that'll be your true resultant vector that you're trying to find. These are a ton of work. You'll remember from last class that the one question we did took like 12 minutes. And I got bad news for you because we're doing another one today. Don't worry, this is going to be like the single longest thing we do today. At least it should be. But I do want you guys to work on this one Please pair up in partners on this. We have a dog that walked 55 meters at 30 degrees north of west, and then 35 meters, 10 degrees south of west. I want you to determine the resultant displacement. That is both a magnitude, which is a number of meters, and a direction for this dog. Anyway, pair up with someone, pause the video here, give it a try. All right, I'm gonna go over this one now. Hopefully that took less than 20 minutes, but well, I won't hold my breath. These do take a long time. So here we go. I'll see how fast I can go through this just for the sake of getting it done. First things first, draw a picture. Try to make the picture about as accurate as you can. It'll make it easier in the long run. It doesn't have to be 100% perfect though. So starting with 55 meters, 30 degrees north of west. Well, north of west, we got to go west first. So I'll do my dotted line for west. And then we're going 30 degrees north of that. That's a reasonable amount, I'd say, about that. And we'll say that right there is your 55 meters. So 55 meters, 30 degrees north of west. Now from there, we're going 35 meters, 10 degrees south of west. So this is where that dog decided to change direction. It's going 10 degrees south of west. So from this point, continue going west, but then we're going just a measly 10 degrees south of that. That's not very far south of it. It's just only about that much. And as a matter of fact, I might have made these dots a little too long because I want this arrow to only be 35 meters. So it's going to need to be like a little more than half as long as that other line. So you know what, I'll shorten that up. Sorry about that. There we go. That'll be a little better. 10 degrees south of that, I would say that's probably more fair. That right there would represent 35 meters at 10 degrees south of west. Now here's the whole idea. We ultimately want to get a resultant vector. In other words, we want to go from our starting point to our ending point and have that just as a direct, straight line. But in order to do that, as you can imagine, we're going to need a y component and an x component. Those are going to be our total x and our total y. So we need to find the x and y components of the original triangles that were set up in order to do that. So I'll change color one more time to green. Let me label all these, try to see just the red here, because I'll label the original red triangles. We'll call this one x1, we'll call this one y1, this will be x2, and this will be y2. So we got 4 different things we got to find here before we can start combining it together. Here we go, right? I'm going to focus on x1 first. Notice x1 is the adjacent side, and we know the hypotenuse. Well, from SOHCAHTOA, I'll write it up here just so we have it, SOHCAHTOA. From SOHCAHTOA, since that's our adjacent side and we have a hypotenuse, we got to use cosine. So it's going to be cosine 30 equals x1 over 55. To solve for x1, just multiply by 55 on both sides. So 55 times cosine 30 gives me, and do not round this until the very end, so just keep as many decimals as you're comfortable with. I think 47.631 is probably enough. If you kept more, kudos to you. That is awesome, right? So 47.631, that's meters to the west. There we go. Now I'll find y1. y1 is the opposite side. Opposite's going to use sine. So we're going to have sine 30 equals y1 over 55, multiply by 55 on both sides, and you're going to get a relative, actually a very nice number, 27.5 meters, and that looks like it's to the north. There we go. Okay, moving on to our 2's now, x2 and y2. Notice x2 in this case, this is a bit of a weird one. It is our adjacent side still. It's just on the other side of it here, but it's not opposite from that 10 degrees. It's still adjacent. So since x2 is still adjacent, we're going to use cosine yet again. It's going to be cosine 10 equals x2 over, that one's hypotenuse is only 35. Multiply by 35 on both sides. So 35 times cos 10 gives me, again, keep as many decimals as you're comfortable with. I got 34.468. And that's meters. And once again, that's meters to the west. That makes it convenient. It's in the same direction as that other one. As for our y2, that's our opposite. So we're going to use sine again. So sine 10 equals y2 over 35. Multiply by 35 on both sides. And you're going to get y2 equals 6.078 is how that would round. 6.078, and that's meters. But watch this one. This time around, that's meters to the south. Okay, so we're almost there. I'm going to switch colors here just so I can show you that this is going on the resultant. we need to combine our X and Y components together now. The X components are nice because they're both in the west direction. So for our X3, which I'll call this bottom one here, and this one will be Y3 going up here. For X3, we just have to add X2 and X1 together. So X3 is going to equal 47.631 plus 34 plus 4 or 0.468. And this is going to give me X3 equals, give me a second here, 47.631 plus 34.468. This is going to give me 82.099 meters west. We can do the same idea for Y3. I'm going to just divide this here. So Y3 is going to be Y1 plus Y2. But just notice Y2 is going in the other direction. Since Y2 is smaller, I'm going to make that one negative. Okay, because it's going to the south, it's going to be in the opposite direction, and it's a smaller number, I'll make it the -1. So north will be our positive direction here. Anyway, so I'll say 27.5 meters. That's how far we went north, minus 6.078. That's how many meters we went south. This gives me Y3 equals, give me a second here. That gives me 21.422 meters to the north, because north took over here because we went further north than we went south. All right, last thing up here. We want to find that resultant vector. That's that diagonal line. Notice there's a right angle here in the corner. That diagonal line is our hypotenuse. We already have the other two sides of this right triangle. You might as well use Pythagoras to find the rest of this, right? Might as well do it. So to wrap this up here, we'll get the magnitude, then we need the direction, but to almost wrap this up here, let's just use Pythagoras. A squared plus B squared equals C squared. So in this case, that's 82.099 squared plus 21.422 squared is going to equal our hypotenuse squared. So we'll just call it C squared. Bear with me here. This is going to take a second. So throw all this in your calculator. This is going to give us a really crazy, like 7,199. I'm not even going to bother writing it down. You got to square root it. Square rooting both sides, you're going to see that C equals, and this time we can round to our sig digs. There's no ifs, ands, or buts here. It's just 2 sig digs. That's going to be 85 meters. That is our magnitude. We now need our direction. Our direction is just our angle. The angle in the corner is theta. Notice we have all three of the other sides of this triangle, but we might as well use the more exact ones. In other words, X3 and Y3. Y3 is our opposite side. X3 is our adjacent side. We're looking for an angle. We have to use a trig ratio for that. You can only find angles using trig ratios. Since we know our opposite and adjacent to a really good degree of accuracy, opposite and adjacent are used for tan. So I'm going to say tan theta equals opposite. That was Y3. Y3 was 21.422. That's where it says over here, right? Over the adjacent side, which is X3, that was 82. There we go, 82.099. Now, hopefully you remember how to dig a theta out of a tan. In order to do that, you have to take inverse tan of both sides. So if you take inverse tan of both sides, you're going to see that theta equals the inverse tan of 21.422 divided by 82.099. And finally, rounded to 2 sig digs, we get 15 degrees. Let's wrap this up as a final answer just so we can throw it all away here. So our resultant displacement is 85 meters. And then in square brackets, because it's our direction, 15 degrees. And then think about what you're doing here. So you're going 15 degrees above west. So that's north of west. So just imagine how you'd form that angle. You'd go this way first and then up. So you went west and then north. So it's 15 degrees north of west. That's our final answer. Like yesterday, I'll put some stars around it. You know, highlight it if you want to. Be proud of that answer. That is an answer that you worked very hard to get. But that's where we're at with this. Whew. Okay, so hopefully, I don't know about you, but hopefully that's a lot better than it was yesterday. I thought that question went a little bit better than yesterday's question does. It's a lot of work, but if you focus on your end goal, and you focus on getting all of your little components and putting them together, it just builds as you go. It seems like a ton because it is a ton of work, but there really is just one goal you're trying to get to. Get all of your X and Y components and throw them all together. Anyway, we have a little bit more we got to do today. That'll be hopefully the longest question of the day. The last concept that we have today is something called relative motion. This is basically the 2D vector stuff we've already been doing, just with more of a real world context to it, or at least a better real world context. That's not quite perfect, but you'll get the idea in a second. I'll just stop rambling here. So first of all, to understand relative motion, I want you to imagine two scenarios. In one scenario, a boat is crossing a river without a current. It's just completely flat water. In the other, however, there is a current. In those pictures you see there that are moving, the current one, of course, is the one on the top, and the one without a current is the one on the bottom. Now, in both scenarios, the boat, or at least the people in the boat, will feel, not relative to the shore, but feel as though they're following a straight line across the river, right? Their boat, as long as the motor is running or whatever, they're probably going to be pointed right to the opposite bank. However, in the scenario with a current, the boat will get dragged down the stream unless it corrects its course, of course, right? So relative to the things on the shore, if there's any bushes or anything on there, you're going to see you actually are going downstream. But in the boat yourself, you're going to feel like you're going a straight line because you're pointed in a straight line. It's just the current is pointing or pushing you down the river. Now, the impression that the boat is going straight in each scenario is known as relative motion. It's the motion measured with respect to an observer. So the observer in the boat in either situation will feel like they're just going in a straight line. However, to someone on the shore, it would be very clear that the person in the boat on the current river is not going in a straight line. So the motion of these objects is relative to whoever is watching this object move, right? Another similar idea to this, like this idea of relative motion, is the idea that right now, as we're sitting or standing here on Earth, Earth is rotating at a very rapid rate. We don't feel like it is, though. We have no perception of that, other than if you look at the stars in the night sky and see how they move as the night goes on, or if you look at the sun in the day sky, of course, and see how that moves as the day goes on. Aside from that, we don't have any basis to say that we're moving, right? It's a similar concept to that. Maybe that point drives it better than a current, because let's be honest here, if you're in a boat, you're going to see the shore, you're going to see that you are actually going downstream, but whatever. Hopefully you get the idea. Anyway, we need to deal with this with a couple classic examples. Do not worry, these examples will not nearly be as long as that one we just did a few minutes ago, and we're going to work on these examples together. So here's the first one. Suppose an airplane is flying at 550 kilometers an hour north. Now, there's a wind from the west, so it's blowing to the east, but it's coming from the west, blowing at 40.0 kilometers per hour east, and it's pushing the airplane. Find the velocity of the airplane relative to the ground, right? Relative to the airplane, we already said it. Relative to the airplane, we know the airplane's going 550 kilometers an hour north. The pilot's pointed north. He's all good, right? He's going 550 kilometers an hour. At least that's how he thinks, right? But the velocity of the plane relative to the ground, however, tells a different story. Because if you were on the ground, you see that that plane's probably going to get pushed by that wind a bit. Now, in reality, of course, pilots know to correct for the wind. It's no different than driving on a highway on a windy day. If you drive on a highway on a windy day, I can at least talk about the highway between the school and the city. If it's really, really windy, I do feel like I have to turn my steering wheel into the wind a little bit to counteract that. But anyway, here's how we go about these questions. So we know the airplane is flying at 550 kilometers an hour north. That's the direction they're pointed. So I'm going to start by drawing a plane that is pointed straight north, right? And I'll just do it with a vector. That's going to be 550 kilometers per hour, right? That's how the plane is pointed. However, we got that wind from the west blowing at 40.0 kilometers an hour east. So it's pushing it to the east. East is to the right. I want to make this kind of to scale, so I'm only going to draw it much smaller than what that much larger 550 kilometers an hour was. So that is 40.0 kilometers per hour to the east. Now, relative to the ground, that plane ended up following a diagonal motion. So what we're trying to find here, and I'll just change color so it pops out, what we're trying to find is that relative motion of the airplane. So in other words, the resultant vector. Now, in the previous examples we dealt with, we were dealing with just distance. So I might have said kilometers, or I might have said meters. This time we're dealing with velocity. Here's the good news. Velocity can still work with Pythagoras on this, as long as you're not given different caveats like, oh, it went for an hour and then this blew for half an hour. That makes things too complicated. But if we're just talking in general terms, your velocity will still be affected through Pythagoras. So what I'm getting at here is, because we have a right triangle, why don't we just use Pythagoras to find the velocity of that airplane relative to the ground? Keep in mind this word velocity though. Velocity is a lot more than just speed. Speed would just be the number, the magnitude, right? Velocity is a vector though, so it also needs a direction, just like these guys had. The only difference is this one is two-dimensional. Anyway, we'll get to that. Let's start by finding the magnitude by using Pythagoras. So Pythagoras would say that 550 squared plus 40 squared is going to equal c squared, c being our hypotenuse, right? Throw that in your calculator. 550 squared plus 40 squared gives us, you know what, I will write this number just because we got room, 304,100 equals c squared. And of course, we don't want that. We want c, so we got to square root both sides. So square rooting that gives us, looks like we need 3 sig digs here. So for 3 sig digs, we've got c equals 551. Ooh, what a boost it got over that 550, huh? 551 kilometers per hour. That's funny. I actually didn't know it was going to be that pathetic. Wow, that hardly got a boost at all. Okay, so 551 kilometers per hour. The main interest of this question, though, is we need that direction, right? Just like that question we did a little while ago, notice what you've already got. It's not a good idea to use this rounded answer. Use the stuff that you were given. It's much safer, right? Notice that this 40 is our opposite, and this 550 would be our adjacent, because this guy's our hypotenuse. So if we were given the opposite and the adjacent from SOHCAHTOA, I won't always write SOHCAHTOA, by the way. I'm starting to get sick of writing that a million times, but it is what it is. From SOHCAHTOA, opposite and adjacent, we're going to use tan, right? So tan of that mystery angle right there, tan of theta is going to equal opposite, which is 40, over adjacent, which is 550. Just like before, we want to get theta by itself, take inverse tan of both sides. That's going to get that for you, no problem, right? So inverse tan of 40 over 550, and we want 3 sig digs. That's going to give me 4.16 degrees. We got to combine this into a final answer though here. So our final answer will be, it's going 551 kilometers per hour at a direction, so square bracket, of 4.16 degrees. And then think about what you're doing here. You're going north and then east, north and then east. So that's 4.16 degrees east of north. I know how backwards that is. You went north and then east, but that means you're going 4.16 degrees east of pure north, right? That's where it really becomes a hurdle. Some people really have a hard time with that. Just remember, you went north and then east, so it was 4.16 degrees east of north. Okay, anyway, that is our final answer. Told you guys that one wouldn't be quite as long. We got one more we're going to do here though. It's a similar one. I'll just give you a bit of a spoiler. We're going to be looking for something a little different this time, but it's a very similar question. An airplane is approaching Calgary directly from the east. It is cruising at an air velocity of 700 kilometers per hour. A strong wind from the south is blowing at 90.0 kilometers per hour to the north. Quite the strong wind, of course, there. Find the precise direction the plane should point in order to compensate for the wind. Okay, so in this question, the plane isn't at the whims of the wind like it was here, where it's getting pushed off track. In this one, we want the pilot to have corrected this by pointing and traveling through the air at some weird direction so that they go, well, they're directly from the east, so they go true west is what we want, because if we're coming from the east, we're going west. Let's draw a picture of this. So here's what we want. We want a resultant vector going straight to the west. This is what we want here. We want to know what's going on, right? Or that's the path, rather, we want to take. What we're looking for is the precise direction the plane should point in order to compensate for the wind. This arrow I just drew is our resultant vector, where the plane is actually going to go. So in other words, we have to have some arrow coming from here, and then some arrow leading to the tip here. The arrow leading to the tip here will be the wind coming from the south. So the wind coming from the south will be coming from the south like that. It'll be pointed to the north. Therefore, we want the airplane to go some diagonal path like that, so that the wind points it or pushes it back up north to force it to go straight west. That's going to be our triangle here. And I want you to notice your right angle is right up here in the corner. Now, let's fill in the numbers we know. I think the obvious number that we know is the wind from the south, 90.0 kilometers per hour. That one's clear. The one that might confuse people, though, is this cruising at an air velocity of 700 kilometers an hour. Remember what I said earlier about how whether you're in the boat or whether you're in the plane, you're pointed in direction, you got your motor set to a certain speed. That's what you believe you're going. This pilot has already corrected his course. So he is pointed diagonally a little bit to the southwest. So that southwest direction, this diagonal here, that will be his 700 kilometers per hour, because that is the direction that he's pointed to make sure he compensates for the wind. Now the wind is going to be pushing back on him. So it'll speed him up or it'll slow him down. I think it'll probably slow him down here because he's pushing into the wind a bit. Oh, actually, I know it'll slow it down here because 700 kilometers an hour is the hypotenuse. That has to be the biggest side. But anyway, we want to find that precise direction the plane should point in order to compensate for the wind. Now, notice the question is just asking for a direction, not a magnitude. The magnitude wouldn't even be relevant here because it would just be the speed that you're going along true to the west, right? And it's not looking for that. It just wants the direction the plane should be pointed. So we're just looking for this angle down here. I'll make that a little clearer. There we go. That angle right there, right? Let's take stock of what we got here. If this angle is what we're interested in, focus on the other parts of this triangle that we've got. I think it should be pretty clear that since 90 kilometers per hour is directly across from this angle, that this side is our opposite. So we have an opposite side. And then hopefully it's also pretty clear that the 700 kilometers an hour being directly opposite of the right angle, that's our hypotenuse. So since we have opposite and hypotenuse, all right, SOHCAHTOA, one more time today, SOHCAHTOA. Since we have opposite and hypotenuse, that means we're going to use sine because it has opposite and hypotenuse in it. Let's go from there. So sine of our unknown angle equals opposite, which is 90, over hypotenuse, which is 700. And as we hopefully are used to by now, to get theta all by itself, we just need to take inverse sine of both sides. Inverse sine, we'll get rid of sine here. Inverse sine, just because you got to do the same on the other side of the equation, right? Anyway, inverse sine of 90 divided by 700. This is going to give me theta equals to 3 sig digs here, 7.39 degrees. And I guess we really should wrap this up by also saying what direction, like in compass directions this is. Notice by how this is pointed, that's just below west. So I would call that 7.39 degrees. It's below west. So I would say that's in brackets south of west. Okay. That was a weird one. These questions are really, really weird. I don't really like these ones where you have to like correct it because they do take a little bit of extra work. But again, I know you guys hate me saying this, but it comes with practice, right? It is what it is, right? Anyway, that was a fairly shorter video from last class, still not short by any means, but here's your practice for today. I want you to continue working on that linear and collinear vectors handout from last class. It was a pretty long one, so if you haven't cleared it by now, I would not blame you. Like, it was a long handout, not to mention a long lesson yesterday. But I do have a new handout just in case you happen to finish that. It's called the Navigation Vector Worksheet. And then just out of curiosity, if you want to see some more diagrams about this stuff, the textbooks, which I have a storage of them right behind the teacher desk there, feel free to like borrow one, but not take it out of the room. Sections 2.2 and 2.3 in the textbook have some diagrams that might actually help you reinforce a lot of this stuff. Anyway, as always, if you have any questions, reach out to me over Remind or over Google Classroom, or even just send me an email. Best of luck, guys.